For the differential equation dy dx equals xy, y is negative 2 when x equals 1, estimate the value of y when x equals 3 using h equals 1. Check by solving the equation and computing y when x equals 3. So, we can identify our x0, y0 as being 1, negative 2. dy dx evaluated at 1, negative 2 is, since this is xy, 1 times negative 2, which is negative 2. Our delta y is then going to be negative 2 times 1, which is a large step length to use, which is negative 2. And that takes us to our next point. Since h is equal to 1, it will be 1 plus 1, which is 2. And we've got negative 2, take away 2 is negative 4. So our next gradient is going to be at 2, negative 4, which is going to be negative 8. The delta y then is going to be negative 8 times 1, which is negative 8. Taking us to our next point, 2 plus 1 is 3. Negative 4 add negative 8 is negative 12. So we're estimating here that y of 3 is negative 12 using Euler's method. So what about when we solve the equation? So it's a separable equation and we get 1 over y dy is equal to x dx, separate and integrate. So we get ln y is equal to x squared over 2 plus a constant. So y would be equal to e to the x squared over 2 plus a constant, which, remember, using index laws is e to the x squared over 2 times e to the c. So we could say that that is a e to the x squared over 2. Negative 2 is going to be a times e to the half, and therefore a is going to be negative 2 e to the negative half. So we have y is equal to negative 2 e to the negative half e to the x squared on 2, and we want y of 3, which is negative 2 e to the negative half e to the 9 on 2. Calculating that, as you can see on the left, is negative 109, approximately negative 109. So nowhere even close to the Euler estimate, which was negative 12. We've gone a long way from the curve. And that's because look at the structure of this solution. This is going to be a very, very steep curve, and the gradient is going to change very quickly. We took a long step length of 1. So we've got this curve that's going to start going up very steeply, but then we take a long tangent here. And then we would take another long tangent here, where this is getting even steeper. So that's why you go a long way away and why using large step lengths are bad. But you might get them in a test or in the exam just simply because it's easy to compute and show the method. So I've set this one up on the class pad here, and if I generate here, we're talking 2 steps is negative 12, like so. But once again, I can make this much smaller. So 0.001, for example. And of course, I need to multiply here by 0.001 as well. And then let's generate and see how we go with this one. So that's at -8, but we've only gone to x equals 2. So I need to actually go to 2000 here. And then let's go to the top and regenerate and see if it's any better. So we need to go right the way down to the bottom when x is 3. -108.6. It's pretty good. So step length is very important.